All right. Hi, everybody. Can you hear me okay? All right. My name's Dean Draco. My partner, Shiv Sakan, is sitting there. We founded IC Manage as a data-centric company back in 2003, focusing on design, data, and IP management. Since then, we've expanded into big data analytics with a leadership position there in EDA, and now with the introduction of our Pia Cash product, high performance computing scale out for I/O.
Linda wants you.
One of the things we're going to talk about today is our Pia Cash for hybrid cloud bursting. What it allows you to do is automatically run your existing workflows in the cloud. And what we're talking about is your existing workflows, those scripts, those thousands, those millions, those trillions of lines of stuff that you've crafted and created over the years without actually having to modify them to burst the jobs into the cloud. Okay, this is a pretty cool time to be in the chip design world, okay? We're in a place where a lot of new companies are entering the fray to design chips. Amazon, Facebook, Google, a lot of new startups, okay? Everything's moving fast with semiconductors, with AI, IoT, and the automotive tech. It's a time of rapid change and brings an explosion of data to what we're doing. Let's see here. Okay. This impacts all of us, and design teams, verification teams, CAD and IT, and the EDE vendors who are trying to meet all of those demands. The challenge that we all face is that as we need more and more computing to do the simulations and the verification and the design, we need more compute. And the capacity planning process typically takes 6 to 9 months. It's a little challenging to get the necessary hardware, get it in place. You have to work with the IT teams, which are not always super cooperative. And the new hardware can become obsolete kind of relatively quickly. So you're often waiting for your jobs to run in the compute farm in order to get your chip out the door. What you really want to be able to do is kind of expand your capacity elastically when you need it. You want to be able to run 500 or 1,000 jobs in the cloud rather than waiting for an overcrowded queue. So this elastic computing need is growing and growing, and as the processors and the CPUs and the designs and the projects get bigger and bigger, it's especially true for the compute-intensive runs like simulation, timing analysis, power consumption, DRC, library, SPICE, all of those different things. The cloud makes the promise, enter the cloud. The cloud promises unlimited compute power on demand. Okay, the cloud providers have made huge investments and have gotten tremendous economies of scale, providing cost savings that can be, we have some customers reporting that they believe it's 10x lower cost using cloud provider solutions. But the challenge, a lot of companies have also completed their due diligence on security. Security's been a little bit of a concern about moving design data into the cloud, but most of that due diligence has been completed, and people are concluding that the cloud is actually more secure. The amount of investment and optimization in the compute farms done by these large-scale companies has outpaced what any single semiconductor company could do. They're into custom hardware, custom data centers, they're building their own buildings, they're locating data centers next to dams to get cheap power, things that you just can't do as an individual company. However, we have, as an industry, a design industry, have a huge investment in our existing workflows, okay? In fact, the workflow of chip design could be considered the DNA of a design organization, okay? These billions and billions of dollars which we've invested in EDA tools and scripts and methodologies, compute farms, etc., are crucial, okay? In order to kind of go and utilize the cloud, we need to be able to leverage the existing things that we have. We can't just throw them out the window, okay, and start over with object-based storage in the cloud. It's not going to really happen, okay? But we still want to leverage the compute capability of the cloud and get that scale. So the solution I'm happy to talk about is what we call hybrid cloud bursting, okay? Hybrid on-premise plus cloud. So it combines the design flow with your existing on-premise compute farm, and it's extremely effective. The design and verification teams continue to run on the existing on-premise compute, but they can temporarily burst into the cloud when they need it. Ideally, the engineers won't even know or care whether the jobs are being run on the local hardware or in the cloud. Now, there's some problems with doing this, okay? There's a lot of details and a lot of complex things that go on in our design environments. At a glance, you might think that you could think about this as a remote site, okay? And you just got to get a little bit of data to the remote site and you can run your jobs. The problem is that it's not a remote site. The compute capacity in the cloud is much, much greater, and the jobs you're running are going to be much, much bigger. The cloud is the opposite. It's actually got a tremendous amount more capacity than your HQ data center. So what does that mean? So in order to enable the cloud to run your workflows, you've got to synchronize up to the cloud tens of millions of intertwined files, okay, that are basically create your design environment. How do you do that efficiently, cost effectively, and quickly? That's the problem. You can't do that using rsync, tar, and NFS. It's just not going to cut it, okay? A lot of people have tried and learned the hard way that it doesn't really work. The way many companies have tried to replicate their existing tools from on-premise into the cloud is you set up your cloud-based environment, you copy a bunch of data up there, you configure and run your system, your tool in the cloud, it crashes and burns because it's missing a bunch of files. You basically then load those files up, try again, crashes and burns, load up some more files, and you keep doing this. It can take weeks, even months to basically figure out all the dependencies to get the right amount of data up there so that you can run this particular job. We've actually had customers try this, and it's taken them months to work through getting their first job to run in the cloud. Not only that, rsync, updating the PDKs, can take hours and hours, if not days, to transfer the data up, okay? And then the question is where do you put the data when you're done? Do you leave it up in the cloud, okay, or do you take it down? So how do you solve all this? Okay, for cloud bursting to be financially workable, the cost factors have to be well understood and controlled. You can buy cheap compute cycles, okay, but if you're inefficient in getting your data in and out, okay, and inefficient in using those cycles, you can destroy the cost advantage that you get with the cloud compute. Cloud storage pricing may not seem particularly prohibitive when you first look at it. It's a few cents, But when you realize that the design environment could be 5 terabytes, 10 terabytes, 50 terabytes, and you're going to move it all up to the cloud and you're going to leave it there, okay, and you start to look at the cost of that storage, it starts to add up very quickly. Okay, if your engineers leave a lot of data laying around, okay, because they might need it or they want to keep it so that they can run that job next week quickly, your costs can actually spiral out of control. Okay, so we're designing really big chips these days. They are really big and complex, okay? The verification and workflows are complex, and we use a lot of NFS mounts, tens of millions of files, 50 terabytes of data, okay? Foundry PDKs, third-party IP, design databases, timing, extraction, all of this stuff all tied together via configuration files, okay? It's a mess. And what that basically means is the combined data need to run your stuff up in the cloud is what we call heavy, okay? There's a lot in it. So rsyncing your design changes or updating PDKs to the cloud can take hours or days. The cloud vendors don't charge you for uploading your data, okay? But it's time consuming, okay? And if it takes a lot of time to get the data up to run the simulation, you negate a lot of the advantage of your ability to cloud burst. So what does that mean? Running actual jobs only typically requires a small fraction of the data, but the question is which data is really needed? You don't know, okay? And that's the trick. The trick is getting the precise minimum amount of data needed to the cloud, transferring it only once, and sharing it among multiple jobs up in the cloud until you're finished, and then basically destroying it so that you're good to go. the design flows are complex, and so extracting the key data is the problem. What exactly is the piece that you need, the isolation data, isolate the data you need, okay? And the design flows are constantly changing, and the data sets are constantly changing, okay? And so kind of figuring it out once, it's good, but then a week later it's changed, and you got to go figure it out again, okay? It's a really hard problem. So we've been developing IC managed Pia Cash for over 5 years, okay? We've had a team developing it in order to basically get really high performance I/O. We have customers now using it, okay? And my co-founder Shiv is going to come up now and is going to share with you more precisely how exactly it all works and how we overcame all of these challenges to provide nearly instant cloud bursting for nearly any EDA job that you might want to run in the cloud. Shiv, take it away.
Cheers.
All right.
Thank you, Dean. So let's go back to that heavy data that Dean mentioned, right? A workflow typically has evolved in your company over a large period of time. You have very large numbers of vendor binaries just to start with. You may have 8 or 10 different versions of every tool that's installed, and the configuration files specify somewhere in your workflow which release of everything that I'm going to work. And often it's a very complex mix. It's not a homogeneous environment, right? On top of that, we have our reference data and our PDKs that contain a lot of stuff. Some of these PDKs can easily span a terabyte, and you could have 10 years worth of them. So there's a lot of this data, and you don't really know which bits of design data are referencing which bits of PDK and which are the vendor binaries that are being run on that flow. So what we introduced, and apologies to any Trekkies out here, but we introduced the Holodeck, right? And what the Holodeck is the ability to project virtually your on-premise environment into the cloud. So you have this, very, deep file trees and configuration environments that are on your on-prem. So when you type ls, right, you've got the whole world, and you see all your different mount points, and you see everything. And what we allow you to do is to just take the metadata representation of that world. So it's extremely lightweight. That metadata representation then allows us to, on demand, based on the application's need, transfer just the files, and not even the files, the bits inside the files, into the cloud. So for example, if you had a large, let's say, a 10 gig file, and I only read the first 10 megs and then appended 100 megs onto the end of it, we would only transfer the little bit and then write back the bit that you wrote onto it. So the key, right, to the Holodeck is that it's essentially indistinguishable from your existing on-premise workflow. So once I've managed to do this magic of the Holodeck, and I've got you there, and you've got everything that you need that's in the cloud, we kind of hit another snag, right? The snag is that typically our EDA workflows are filer-based. We have a shared file workflow model where multiple compute nodes can see each other's results, right? So that they can run successive jobs, or they can enforce a bunch of parallelism like we do, corners and, multiple data gathering approaches so that we can have a top level view. But in the cloud, we have, a very, very high density of compute nodes, and we only have block stores. There isn't really a shared storage or a shared file workflow available in the clouds because that's not how they've evolved or developed. So, how's everybody else doing this? Well, let's look how software did it. That's option one. They rewrote their tools and their flows, right? And they adopted what was called a microservices architecture. This was originally pioneered by Netflix, and their chief cloud architect was Adrian Cockcroft. And they came up with an architecture where you deploy software applications as modular services. So you just slice it all up, and everything's modular, and you share data only at the very end. There's very little sharing that occurs between these services till later. That's very, very impractical for EDA and HPC, high performance compute hardware design. We have way too many interdependencies to modularize, right? It is absolutely almost impossible to say I'm going to slice these big chips into these smaller pieces, because we have to deal with physical issues, physical proximity, and physical interaction at the device layers, right? So we can't slice it up. On top of that, there's a whole bunch of, legacy tools that we've been using for, don't ask me how long, right, that are just essentially impossible to convert. You're not going to be able to rewrite those. At least if you are going to rewrite them, the risk of rewriting them is too big, because, unlike software, we can't ship patches to our hardware. You could roll your own filer, right? Unfortunately, filers are scale up, right? The cloud offers all of this high density compute, which is scale out. So now, if you try and even roll your own filer, you've got this mismatch. You're trying to apply a scale up storage solution or a file solution with a scale out compute. And this mismatch results in the inability for your I/O to keep up, leading your applications to become I/O bound, even though you have all of this compute. We see it already today, right? We see that today on-prem, our filers are really struggling to keep up, and buying more filers isn't really helping us, because our filers are giving us capacity, and they're not giving us the I/O that we need. You could try an external filer, but, that's going to be even worse. You could test a new file system. I believe, I'm not sure exactly, maybe Derek knows the exact number, but I believe there are 20 to 200 storage startups all trying to do something to solve this problem. The reason why is, typically, high performance storage is a multi-billion-dollar market, and a lot of people are trying to go after it. However, if you want to build an HPC, model in the cloud using all flash for semiconductor, you're going to be broke really quickly. You can certainly do it. You can write those big checks. You can get massive amounts of, custom hardware and flash and do it all. But, flash memory fundamentally, from a semiconductor perspective, is not scaling the way magnetic media is scaling, right? So what you end up here is burning a lot of cash. Alternatively, right, we introduce Pia Cash, scale-out I/O that delivers extreme file performance. We have about 70 person-years of development behind the tool. Dean mentioned 5 years. It's probably double that, because there was a lot of thinking that happened before, a lot of architecting, a lot of design. And so what we do is that we take advantage of local NVMe. Right? This is a standard Intel strategy to blur the lines between file I/O and memory I/O. So we use NVMe, but instead of building file systems out of NVMe, we make your local file system look like a cache, right? And we provide a shared storage model for that cache using peer-to-peer. So this enables high-performance compute in the cloud for EDA tools. And by using peer-to-peer between multiple readers and writers, we can now do everything in parallel. Right? Most file systems today that we're using are serialized. There are alternative parallel file systems that have been used in HPC compute for a while, but they've been optimized for different kinds of workloads, which is typically high concurrent I/O, which is not the way EDA works. So what we do is that we use flash as a cache, not as a storage. And it slashes your costs, because using small 1 terabyte or 2 terabytes of NVMe per node, you can now get extreme file performance. We offer 3 simple steps to hybrid cloud bursting. And some people have said to me, wow, I don't believe this. And I tell you, if you don't believe it, come upstairs to booth 2618. we got a nice car there for you to look at, and we'll show you how this occurs and how quickly it occurs, right? You simply, on one of your compute nodes, register your filer mount points and your namespaces to a little agent. That agent then allows you to project your entire corporate data, right, in the cloud. So you type ls, and every mount that exists, everything that you've registered on the left-hand side is suddenly available. And it doesn't take very long because we only transfer the data on demand. So the first ls is just the top level. The second ls is a little bit deeper. You can do a recursive, and it just pulls it all on demand. Once the virtual environment's been created, and the reason you create the virtual environment is so the application sees everything that it needs. It sees its includes, it sees its configuration files, it sees all the things it needs to see, right? But they're all virtualized. And as they're accessed, we pull them over the wire. What we're able to do is to really provide a scale-out solution for I/O, because we're bringing files to the local compute node. We are not going over the network to create a remote file system. We are bringing those files locally through this on-demand caching onto the local NVMe. This gives you a lot of I/O. In fact, more than you know what to do with, right? A standard, Amazon instance, for example, with 2 NVMe's can give you 2 gigabytes per second of I/O. And like something like a C5D 18x large can give you 10 gigabytes. Guys, this is per node, right? So our unlimited aggregate throughput, this is true scale out. But more importantly, it's very, very cheap, because we're not storing your data there. It's transient. We have the job, we run the job, and we get another job in there, right? And storage happens in the background. We're very, very heavily focused on job throughput, job execution, and speed of completing these jobs. Storage is something that happens in the background asynchronously, and we can write it back to wherever you want. We don't care. We're totally agnostic to it. Now, we talked about getting data into the cloud, but obviously getting data out of the cloud is very expensive. All the cloud vendors are the same, $10 a gigabyte. That can rack up really, really quickly. So if you're trying to maintain coherency between your on-premise and your cloud, you have a lot of challenges there, because you want to make sure that what you push down, one, is authorized to be pushed down. You don't want big spice transients going over the wire, right? But you may want your logs and your results files, so you want that controlled. But more importantly, that's, our selective write-backs lets you get that level of control. But most importantly, all writes are saved as deltas. So we know what you wrote. If you appended to a file, we'll just send the appended bits back. If you just modified a file somewhere in between, we'll just send those bits back. We don't have to, oops, I pressed a button accidentally. Yikes. Help. Oh, it came back. There we go. We do not copy back any data that we read over the wire, because we already know what it is, and we know our writes, and we can send those writes back as deltas, so we can keep your costs, under control. However, one of the big challenges is, people worry about attack surfaces. And if you leave complex file systems up in the cloud, I'm not saying they're insecure, it's a large active surface. But if you just use ephemeral caching like we do, when the job is done, the data is gone, it doesn't exist, right? You were never there. And that's the power. Now, one of the accidental discoveries of our architecture very early on was that because we were always translating this virtual layer to a real layer, we know every transaction on a file in file namespace. Storage has typically been in block space. So, your IT guys can tell you that you're getting a very high block rate, but they can't help you identify a specific or local bottleneck in a workflow. Why is this application suddenly running slow? Well, I'm not really sure. But in Pia Cash, we know the name of the file, we know the writer, we know the reader, we know every stat, we know every open, we know every close, we know every rename, we know absolutely everything. And this spews out, a massive log of events that get consumed by something like Elasticsearch, and then you can build your own dashboard. So you can use it not only for optimizing your workflows and finding out, hey, where am I inefficient, which workflows are broken, which workflows are good, which ones can be optimized, but more importantly, you can use it to detect outliers. Right? In this modern science of big data and AI, we're focused around outlier detection. Why did this guy or this team who are usually working 9 to 5 are now working 2 a.m., right? That's an indicator. Or who's this specific individual who used to only do reads in this area is now doing massive reads across hundreds of projects. Data exfiltration, when breaches occur, what tends to happen is that you lose, tons of data because you didn't know about it, right? You don't read about someone, oh, I lost 3 bytes of data, right? You read about people who've lost terabytes of data, the entire corporate databases, Equifax or whatever being the last one, because they don't know. With this outlier detection behavior, you can very, very easily detect what's going on because we're working in file space and not in block space. Now, chains of custody is a very important issue in semiconductor when you're using other people's IP, and you want to make sure that that IP is being used appropriately according to the SLAs you've signed for that data. So it's very simple in Pia Cash to add a simple change of custody, and we just use a distributed ledger in the metadata to track where a file has been. So if we look at some of the results we've achieved, this is a workflow, and we're able to just extract just the job that needs to run. And these numbers are fairly typical, just the bits that you need, right? This is your workflow, but I just want that job. I want to extract that dependency, right? You can burst like crazy because the files you're pulling over are a fraction of what's actually there on your trees. And remember, we can do it at the extent basis. So if you only read, as I mentioned earlier, a few bytes of a file, we'll only transfer those bytes, right? We won't transfer the whole file. We have extent level granularity on individual files as well. And because we're using NVMe caching, we can eliminate those I/O wait states presented by your filers, right? Not only that, we can provide very, very low latency I/O behavior and not variable latency behavior that we see in complex file systems. So that's the essence of Pia Cache for cloud bursting, and I'm going to turn it back to Dean for a little bit of a summary.
All right, well, thank you, everybody. I appreciate you taking the time. So in summary, IC Managed Pure Cache provides hybrid cloud bursting. It allows you to automatically run your existing workflows in the cloud with no changes to your workflow. It gives you an extreme level of file performance that's never been seen before. Sustainable, low-cost deployments to the cloud. Okay. It is application and cloud vendor agnostic. So this will work with Azure, Microsoft, Google, and others. And it is also tool agnostic. So it works with Synopsys, Mentor, Cadence, and all the other vendors here at DAC. It is an advanced file-based analytics and security built in, which will provide you additional data to track down and tune your performance. And at this point, I'd like to thank you. If you have any questions, Shiv and I are here to answer them. And if you want to see a live demo or get further information, please don't hesitate to visit at the booth right here, booth 1240, or upstairs at our second booth. Thank you very much, everybody. Okay, any questions?
Questions? Michael. Well, let's get you a microphone.
Hello, my name is Michael. I am from NVIDIA, and I have a question related to EDA. In my specific use case, we have 10,000 jobs out of a single volume that's going to also depend on other 50 NFS volumes. So I don't see how local cache can help in this case. So how would you address this situation?
So remember that the way the cache works is it creates a virtual file system that has all of the files that you need, right, from a conceptual basis. So if you need to access those files, they are simply loaded on demand. Most applications will do a whole bunch of reads, and at those points, those reads are finished, you can expunge the cache, and you can bring in newer objects, because the way most applications tend to work is that they do reads, they load a memory representation, and they do a bunch of writes. So all of those are available because we support a full peer-to-peer architecture to bring those files in wherever they may be, distributed across your network.
Okay, thank you. I will
Okay.
ask more questions later.
Okay?
Any other questions? Over
We
here.
have one in the corner
Gloria.
there, Gloria.
Gloria, over here. Thank you. Please ask questions.
So is this solution for on-prem or just cloud only?
I'm glad you asked that question. It is absolutely suitable for both on-prem and for cloud, and we have customers using it in both flavors. So you simply need to add, NVMe to your on-prem nodes, and you can run hyperconverged and get massive acceleration on your on-premise as well. The advantage, of course, that why the cloud is particularly attractive right now is the cloud is already fully NVMe capable. So your standard big compute instances, for example, C5Ds on Amazon, have from 2 to 8 NVMEs already on site. But yes, to answer your specific question, it's absolutely beautiful for scaling, on-prem as well.
And for cloud instances, what do I need? If
All
I
you need is a small amount of NVMe.
No, but for
Can we get that a little louder, please?
your solution, do I need a license in that EC2 or a specific type of EC2 instance?
We have a number of recommended instances based on your workload. So those go into autoscale groups, and you just run whatever instances you want, and then you pay us some fixed amount based on those instances.
Okay.
And the reason we primarily are talking about cloud and cloud bursting here in this presentation is because we're in the infrastructure cloud bursting aisle, and that's kind of the topic of the day.
Thanks to Derek.
Thanks, Derek. But the initial deployments that we did with Pia Cash were on-prem for customers who wanted to accelerate their on-prem synthesis and simulation.
I have a question. Does it work only on IC managed control repositories, or?
No, it doesn't care about IC managed repositories. It's got nothing to do with IC managed repositories. It is totally agnostic to where your files are. It works on any domain, anything that uses files, which is every single computer system in the world.
And how do you define what files are needed in the workflow? Is
On
it a
demand.
user input?
So the files are defined by when the application runs, it asks for the file to the file system. That creates the definition of the files that are needed.
Thank you.
So how many production workflows do you have running in the cloud using this capability?
I have to take that under advisement. A lot of our customers don't want us talking about it. So perhaps
I don't need the name. I just want to know if you've got anyone actually using it in production.
we have
There
stuff running in production.
Yeah, there's many different workflows running in production. Any other questions? Oh, over here, Sanjay.
Oh, Chandra.
Oh, Chandra.
Yeah, my question is about the cost. You said about it's 10x cheaper or lower cost to run in the cloud. EDA workloads, my analysis says exactly the opposite. For sustained workloads running in the cloud, it's a lot more expensive.
Yeah, so that number was a number that was reported to us by a customer. They felt that working with some of the cloud vendors, that for them, given their operational costs, that moving to the cloud would save them significant amounts of money, because they felt that Amazon or Azure, or I don't remember who they were working with, but was significantly cheaper once they looked at their fully burdened costs of facilities, people, okay, buying the hardware, power, maintenance, repairs, all of the things. When they fully kind of burdened it, they felt that they were on the order of 10x more expensive than what they could get from the cloud providers. We were a little surprised by that number as well. It seems a bit high, but you know, who are we to contradict what the customer says?
I should hire the procurement people.
What's that?
I should hire the procurement people so we can do better vendor management.
Yeah. Okay, any other questions? You sure? Okay. Anybody have interest in it? All right. Okay, awesome. All right, we're here if you want to get us. Thank you very much for attending and listening to us. We appreciate it. You guys have been great.
Thank you.